Richter magnitude scale.
The Richter magnitude scale was developed to assign a single number to quantify the energy that is released during an earthquake. The scale is a base 10 logarithmic scale. The magnitude is defined as the logarithm of the ratio of the amplitude of waves measured by a seismograph to an arbitrary small amplitude. An earthquake that measures 5.0 on the Richter scale has a shaking amplitude 10 times larger than one that measures 4.0, and corresponds to a 31.6 times larger release of energy. Since the mid-20th century, the use of the Richter magnitude scale has largely been supplanted by the moment magnitude scale, MMS, in many countries. However, the Richter scale is still widely used in Russia and other CIS countries. Earthquake measurements under the moment magnitude scale in the United States, 3.5 and up, on the MMS scale, are still usually erroneously referred to as being quoted on the Richter scale by the general public, as well as the media, due to their familiarity with the Richter scale as compared to the MMS.
Development.
Developed in 1935 by Charles Francis Richter in partnership with Benno Gutenberg, both from the California Institute of Technology, the scale was firstly intended to be used only in a particular study area in California, and on seismograms recorded on a particular instrument, the Wood-Anderson torsion seismograph. Richter originally reported values to the nearest quarter of a unit, but values were later reported with 1 decimal place. His motivation for creating the local magnitude scale was to compare the size of different earthquakes. Richter, who since childhood had aspirations in astronomy, drew inspiration from the apparent magnitude scale used to account for the brightness of stars lost due to distance. Richter arbitrarily chose a magnitude 0 event to be an earthquake that would show a maximum combined horizontal displacement of 1 0.00004 in, on a seismogram recorded using a Wood-Anderson torsion seismograph 100 kilometers, 62 miles, from the earthquake epicenter. This choice was intended to prevent negative magnitudes from being assigned. The smallest earthquakes that could be recorded and located at the time were around magnitude 3. However, the Richter scale has no lower limit, and sensitive modern seismographs now routinely record quakes with negative magnitudes. Local magnitude was not designed to be applied to data with distances to the hypercenter of the earthquake greater than 600 kilometers, 373 miles. For national and local seismological observatories, the standard magnitude scale is today still. Unfortunately, this scale saturates at around equals 7, because the high-frequency waves recorded locally have wavelengths shorter than the rupture lengths of large earthquakes. To express the size of earthquakes around the globe, Gutenberg and Richter later developed a surface wave magnitude scale and a body wave magnitude scale. These are types of waves that are recorded at teleseismic distances. The two scales were adjusted such that they were consistent with the scale. This succeeded better with the scale than with the scale. Both of these scales saturate when the earthquake is bigger than magnitude 8, and therefore the moment magnitude scale was invented. These older magnitude scales have been superseded by methods for estimating the seismic moment, creating the moment magnitude scale, although the older scales are still widely used because they can be calculated quickly.
Details.
The Richter scale was defined in 1935 for particular circumstances and instruments. The instrument used would become saturated by strong earthquakes and unable to record high values. The scale was replaced by the moment magnitude scale, MMS. For earthquakes adequately measured by the Richter scale, numerical values are approximately the same. Although values measured for earthquakes now are actually MMS, they are frequently reported as Richter values, even for earthquakes of magnitude over 8, where the Richter scale becomes meaningless. Anything above 5 is classified as a risk by the USGS. The Richter and MMS scales measure the energy released by an earthquake. Another scale, the Mercalli intensity scale, classifies earthquakes by their effects, from detectable by instruments but not noticeable to catastrophic. The energy and effects are not necessarily strongly correlated. A shallow earthquake in a populated area with soil of certain types can be far more intense than a much more energetic deep earthquake in an isolated area. There are several scales which have historically been described as the Richter scale, especially the local magnitude and the surface wave scale. In addition, the body wave magnitude and the moment magnitude, abbreviated MMS, have been widely used for decades, and a couple of new techniques to measure magnitude are in the development stage. All magnitude scales have been designed to give numerically similar results. This goal has been achieved well for and. The scale gives somewhat different values than the other scales. The reason for so many different ways to measure the same thing is that at different distances, for different hypercentral depths, and for different earthquake sizes, the amplitudes of different types of elastic waves must be measured. Is the scale used for the majority of earthquakes reported, tens of thousands, by local and regional seismological observatories. For large earthquakes worldwide, the moment magnitude scale is most common, although is also reported frequently. The seismic moment is proportional to the area of the rupture times the average slip that took place in the earthquake, thus it measures the physical size of the event is derived from it empirically as a quantity without units, just a number designed to conform to the scale. A spectral analysis is required to obtain, whereas the other magnitudes are derived from a simple measurement of the amplitude of a specifically defined wave. All scales, except, saturate for large earthquakes, meaning they are based on the amplitudes of waves which have a wavelength shorter than the rupture length of the earthquakes. These short waves, high-frequency waves, are too short a yardstick to measure the extent of the event. The resulting effective upper limit of measurement for is about 7 and about 8.54. New techniques to avoid the saturation problem and to measure magnitudes rapidly for very large earthquakes are being developed. One of these is based on the long-period P wave, the other is based on a recently discovered channel wave. The energy release of an earthquake, which closely correlates to its destructive power, scales with the 3/2 power of the shaking amplitude. Thus, a difference in magnitude of 1.0 is equivalent to a factor of 31.6 in the energy released. A difference in magnitude of 2.0 is equivalent to a factor of 1000, in the energy released. The elastic energy radiated is best derived from an integration of the radiated spectrum, but one can base an estimate on because most energy is carried by the high-frequency waves.
Richter magnitudes.
The Richter magnitude of an earthquake is determined from the logarithm of the amplitude of waves recorded by seismographs. Adjustments are included to compensate for the variation in the distance between the various seismographs and the epicenter of the earthquake. The original formula is where A is the maximum excursion of the Wood-Anderson seismograph, the empirical function AO depends only on the epicentral distance of the station. In practice, readings from all observing stations are averaged after adjustment with station-specific corrections to obtain the value. Because of the logarithmic basis of the scale, each whole number increase in magnitude represents a tenfold increase in measured amplitude. In terms of energy, each whole number increase corresponds to an increase of about 31.6 times the amount of energy released, and each increase of 0.2 corresponds to a doubling of the energy released. Events with magnitudes greater than 4.5 are strong enough to be recorded by a seismograph anywhere in the world, so long as its sensors are not located in the earthquake's shadow. The following describes the typical effects of earthquakes of various magnitudes near the epicenter. The values are typical only and should be taken with extreme caution, since intensity and thus ground effects depend not only on the magnitude, but also on the distance to the epicenter, the depth of the earthquake's focus beneath the epicenter, the location of the epicenter and geological conditions. Certain terrains can amplify seismic signals. Based on U.S. Geological Survey documents, the intensity and death toll depend on several factors: earthquake depth, epicenter location, population density, to name a few, and can vary widely. Minor earthquakes occur every day and hour. On the other hand, great earthquakes occur once a year, on average. The largest recorded earthquake was the Great Chilean Earthquake of May 22, 1960, which had a magnitude of 9.5 on the moment magnitude scale. The larger the magnitude, the less frequent the earthquake happens.
Examples.
The following table lists the approximate energy equivalents in terms of TNT explosive force, though note that the earthquake energy is released underground rather than overground. Most energy from an earthquake is not transmitted to and through the surface. Instead, it dissipates into the crust and other subsurface structures. In contrast, a small atomic bomb blast, see nuclear weapon yield, will not, it will simply cause light shaking of indoor items, since its energy is released above ground. 31.6227 to the power of 0 equals 1, 31.6227 to the power of 1 equals 31.6227 and 31.6227 to the power of 2 equals 1000. Therefore, an 8.0 on the Richter scale releases 31.6227 times more energy than a 7.0, and a 9.0 on the Richter scale releases 1000 times more energy than a 7.0. Thus, quakes using the more modern magnitude scales will denote their abbreviations, and those that have no denoted prefix are. Please be advised that the magnitude number, example 7.0 displayed for those quakes on this table may represent a significantly greater or lesser release in energy than by the correctly given magnitude, example.
Magnitude empirical formulae.
These formulae are an alternative method to calculate Richter magnitude instead of using Richter correlation tables based on Richter standard seismic event, equals 0, A equals 0.001 mm, D equals 100 km. The Lilly empirical formula, where A is the amplitude, maximum ground displacement, of the P wave, in micrometers, measured at 0.8 Hz, is the epicentral distance, in km. For distance less than 200 km. For distance between 200 km and 600 km. Where A is seismograph signal amplitude in m, D distance in km. The Bistriczany, 1958, empirical formula for epicentral distances between 4 at to 160 at. Where is magnitude, mainly in the range of 5 to 8. Is the duration of the surface wave in seconds, is the epicentral distance in degrees. The Tsumura empirical formula, where is the magnitude, mainly in the range of 3 to 5, is the total duration of oscillation in seconds, is the epicentral distance in kilometers. The Tsuboi, University of Tokyo, empirical formula, where is the magnitude, is the amplitude in is the epicentral distance in kilometers.